Hey guys, in this video I'm going to talk about the graphical representation of one-dimensional motion under constant acceleration. So remember that generally position, velocity, and acceleration, these are vector quantities, but because I'm restricting to just one-dimensional motion for now, I'm going to write them as scalar quantities. Also recall that we've defined, once you have the position of an object, so the position I'm thinking of a point-like object, the point which represents an object, that also assumes you have a coordinate system of some kind, so that tells you what the position vector actually is. If you have that, you can find the velocity of the object by just taking a derivative with respect to time of the position, and you can find the acceleration by taking a derivative with respect to time of the velocity. So there's like a chain here, right? We start with position, and then we go down and take a derivative and we get to velocity, take a second derivative, and we go down and get to acceleration. Well, if you remember from your calculus class, there's a very nice graphical representation of what taking a derivative means. If you have a graph of position, taking a derivative just means finding the slope of that graph. So going from position to velocity is finding the slope of a graph, and then going from velocity to acceleration is again finding the slope of another graph. So it's a very nice graphical representation of taking a derivative and going from position, velocity to acceleration. Now there's also a way of going backwards. Just like from here to here is a derivative and from here to here is a derivative, there's such thing as an antiderivative that's taking an integral, which you should also know from calculus. So if you go backwards from acceleration, you integrate the acceleration, you get velocity, integrate the velocity, you get position. So I can go backwards as well. And just like the slope is a nice graphical representation of taking a derivative, there's a nice graphical representation of integrating something, and that's finding the area underneath the curve. So I'm going to write area here. So now I'm just going to show you a couple examples of how you would go about, if you had a graph of an object's motion, how you would do this process to determine one of the other quantities if you had a graph of one of them. So if you had a graph of the velocity, how could you find the position and acceleration? Or if you had a graph of the position, how could you find the velocity and acceleration?
Okay, so recall the chain here. We start with the position, take a derivative, get to the velocity, take a derivative, get to the acceleration. These are derivatives with respect to time, so the slope goes from here, find the slope, get this, find the slope, get this. The integral goes back the other way, start with the acceleration, integrate it to get the velocity, and then integrate it to get the position. So these are finding areas and these are finding slopes. So for a quick illustration of this concept, here's a graph of the velocity in the x direction with respect to time. You can take this as like a car, for instance, where it starts with zero velocity and then the velocity gets bigger and bigger and bigger in a linear way, and then I hit some point and then I keep moving with a constant velocity. And so I'm going to use this information about velocity to determine the acceleration and the position. Now if we go up to our little picture here, starting with the velocity, we want to go to the acceleration. That means taking d dt. And so what I'm going to do is I'm just going to write this and write slope, because we're going to use the slope to find the acceleration. And if we want velocity and go back to position, then we have to take the integral. So then I'm just going to write this and write area. So I'm going to start with the slope because the slope is generally a little bit easier. I want to know what the slope of this line is at every point, right? Because I need to say what the acceleration is at this time, at this time, at this time, at this time, and so on. This is a constant straight line, so it has a constant slope. It's moving upwards, so it has a constant positive slope. I don't know what it is, but I certainly know that it's some constant positive value. So I'm just going to say, okay, it's whatever scale my acceleration is, it's right there. And it's going to be like that all the way until the stopping point of the velocity plot. So now what's the rest of the plot going to look like? Okay, starting from this point, we have a constant velocity. That's a line with slope 0 because it's not going up or down. And so my acceleration is going to drop to be 0 at that point. And it's just going to go along like this. So then the question is, what do we do in between these 2 points? What do we do from here to here? Well, mathematically, the best answer is probably to put a little circle there. Because what you're doing is you're saying, okay, what is the acceleration? What is the slope of a line right here? Well, the slope right there is undefined because it's either a positive number here or 0. So if something's undefined mathematically, we usually write these little circles. Realistically, it's possible that it might be better to draw some picture where there's a transition, a smooth transition like that. But either way, I would accept either answer as being the correct interpretation of the motion that's going on. So going the other way from the velocity to the position is a little trickier because what we need to do is find the area under the velocity curve. So the first thing I'm going to do is I'm just going to break the velocity into chunks, some of which are sort of triangular and some of which are sort of rectangular. So now I need to say, okay, if I integrate the velocity over this interval right here, that's going to tell me the position in this interval right here. So to integrate that, I need to find the area right here. That's some kind of triangular region. And the area in that curve, I could find that if I knew the base and the height by 1/2 base times height, but I know it's going to be some small positive value, so I'm just going to put the x position after that time interval right there. So the next step is to find the area of this next region, but then recall how the integral is defined. It's defined over a limit from 0 to some t. In this region, we went from 0 to t, but now in this region, we want to start from 0 and go up to t. So that means that we need to take this area and add it to this area. So we need an estimate for how much bigger this area is than that area. Well, we can actually see that the original triangle is actually right there. So this looks to me at least to be 1, 2, 3 times as big as the original. So we're starting with 1 and then we're adding on 3. So I just should make this essentially 4 times as big. So I'm going to estimate it to be right about there. And we have to continue that process as we add in more and more intervals. So for the next one, you can sort of see that I can add up 1, 2, 3, 4, 5 of those. So I'm going from the first one is 1. I have 4 here. I add on another 5. So I'm getting even bigger than the original that I started with when I go to the next point. Maybe that's something like that. For this guy, again, it gets even bigger. I got 1, 2, 3, 4, 5, 6, 7. So I started with 4, 9, and I want to add on another 7. And of course, I'm just estimating all these. If you had actual values, you could really do a much better job than me. So the next set of regions are all the same size. These boxes are all going to be the same size. But if we do this little triangle game that I'm playing here, we'll see there's even more triangles here than there, and so I should add in even more. So that's going to be a point, oh, right about there, let's say. But the next region over here is exactly the same size as that as this guy right here. That's the same size, that's the same size. So now I'm just going to keep adding on this same amount. So it's going to increase in a pretty constant and linear fashion. Of course, I'm still going to get off the edge of the plot, but I think you'll see what I'm getting at. Okay, so that's the graph of the motion for as much time as I can fit on my picture. And now I should just connect the dots, and I get a nice curvy thing, which goes up to a linear straight line. Okay, so that's a basic demonstration of how you can use the area and the slope to get any of the various kinematic quantities from the other ones. You could check this too, right? You could say what's the slope at every point along this x graph. You should get an increasing slope, because this is positive and getting bigger and bigger and bigger, and then a flat slope, and that's exactly what happens, right? This slope gets bigger, gets bigger, and then the slope is constant. And then, of course, if you did the slope down here, you'd get our answer. You could go backwards. You could say, okay, here's the graph of my acceleration. The area under this curve should give me this velocity plot, and it will. If you think I have one box here, one box here, one box here, you integrate this, you get that value. You integrate the 2 boxes, you get something twice as big, which is here to there. Do this one, you get something 3 times as big, 1, 2, 3, and you see that it's consistent. So you should be able to either go this way or go that way. Great, thanks guys. This has been a graphical representation of motion. It's a good way to understand the acceleration, the velocity, and the position of objects without having to refer to any specific equations, just by playing around with these graphs.